All right, guys, here we go. We're looking at section 2.2 and 2.3, day 1. This is all involving properties of functions. So first thing we're going to do is look at this graph here, okay? This guy's a function. Now, if we were in class, well, I'd probably give you a minute or two to talk to your teammates about how do you know this thing is a function. Remember, we talked about the other day that every function, for a function, every x value has exactly one y value. Every input has exactly one output. So when you're looking at these points here, right, the x value of 0 only has one output of 4. The x value of 2 pi only has one output of 4. 4 pi only has one output of 4. Right, all these x values only have one output. Even though these points up here are spitting out the same y value, that's fine. You might remember a quick shortcut, the vertical line test. If every vertical line hits this graph exactly one time, then we know this guy is a function. So a few ways we would have reviewed a function. So what we're going to do first is look A through G at just some ways to interpret this graph. First off, up top in letter A, it wants to know f of 0, f of 3 pi over 2, and f of 3 pi. Now, the other day we looked at doing this from the given an equation. If we're not given an equation, we have to use the graph. Remember, this thing here, the 0, is the x value, and basically when we plug that x value in, we end up getting the y value. So if I don't give you an equation, you have to use the graph to get your x, y values. The x value, when the x value or the input is 0, the y value or the output is 4. So f of 0 is just 4. F of 3 pi over 2, right here, when the x value is 3 pi over 2, the y value or the output is 0. And for f of 3 pi, when the input is 3 pi, the output is negative 4. Okay? So that's all we have to do there for that first problem, letter A. Letter B, what is the domain of f? Okay, now some of you guys might recognize this as a sine or cosine function. And if you remember, the sine and cosine functions do have a domain of all real numbers. But be careful, there's no arrows on the end of this. This graph doesn't say anything about one period. So the domain here is restricted. It starts here, stops here. Starts, stops. Okay? So we can't assume domains, graphs go on forever unless it's stated somewhere in the problem. So this domain starts at 0 with a bracket because it's a solid point, all the way to 4 pi. That is interval notation. Okay? Set notation. We'll show this as well, just to get some practice. Values of x such that. And now when we do an x value like this, we want to say x is between 0 and 4 pi. So you might recognize this compound inequality. X is greater than or equal to 0. It's also less than or equal to 4 pi. So there's my set notation. Okay. The range now. Range, if you remember, are the y values. So from the bottom to the top, right, going bottom to top, the lowest y value here is negative 4. And the highest y value is positive 4. Again, brackets because we have a solid point down here and a solid points up there. The range in set notation would be the values of y such that. And the only difference is we're going to use y values instead of x values, but we can write this the same way. Y has to be greater than or equal to negative 4, but less than or equal to positive 4. And there's my set notation. All right, intercepts. So I'm seeing here I have about 4 x-intercepts there. That's what it's asking for, so I'm going to label those as points. Pi over 2, 0. 3 pi over 2, 0. 5 pi over 2, 0. And 7 pi over 2, 0. So if you're in class, most of you would see that. A lot of you would forget about one more intercept, the y-intercept. This problem doesn't say just x-intercepts, it says list all intercepts, so the y-intercept is also a point. All right, let's look at the next few problems. How often does the line y equals 2 intersect the graph? So if you remember, y equals 2 is a horizontal line. Y equals 2 goes across the graph just like this. And we want to know how many times it intersects. So 1, 2, 3, 4 times. All right. For what value of x does f of x equal negative 4? So this one is working on that notation, that function notation. Do you understand what this is asking and what's going on? Right? So we want to know what x value does basically the y value equal -4? All right, so if I look into my graph, I'm looking for y values of -4. On this domain, it happens twice, at pi and 3 pi. So this happens when x equals pi and 3 pi. Okay? For what values of x is f of x greater than 0? Okay? Well, here's what I think most people, not most people, but some students would say in class, and this is actually a good mistake. A lot of students would think these 3 points up here, right? They would say 0, 4, 2 pi, comma 4, and 4 pi. I'm sorry, this one only wants the x value. So you'd say 0, 2 pi, and 4 pi, okay? What you got to watch out for here is that on graphs, there are infinite number of points on each curve. Any curve or line you draw has infinite number of points. So all of these blue points I'm putting here have y values that are greater than 0, okay? So how am I going to describe an infinite number of y values or a lot of y values? I'm going to use interval notation. So to describe this first piece of the graph, that everything I just shaded there has y values greater than 0. So to describe that, interval notation or x values, so I'm going to go from bracket 0, comma, all the way to pi over 2. Now, I used a bracket at the first x value, 0, because there is a point up there. At pi over 2, though, I have to use a parenthesis because this inequality is not equal to. I don't want to equal 0. I just want to be greater than 0. Okay? Second interval here, I'll shade it, kind of color code it. Every point there on that little piece of kind of the upside down parabola has a y value greater than 0, so that we're going to union that with everything from 3 pi over 2 to 5 pi over 2. Now again, these are not points. This is interval notation. Last but not least, this little green segment, or not segment, but piece of the graph over here. So we're going to union that with everything from parenthesis 7 pi over 2. Again, I have to use a parenthesis there because I can't equal 0. And then all the way to 4 pi with a bracket because this point where the x value of 4 pi is greater than 0, so I can include that point. Okay. So that's a good problem, just looking at a function, graph of a function and interpreting the function notation. The unique thing about these last few A through G here was that there was no equation. Everything had to be done from the graph. Okay, quick theorem. A function is even if and only if it's symmetric to the y-axis. Okay, so even functions are symmetric to the y-axis. The easiest even function to picture is a parabola, right? If you draw the line of symmetry right down the middle, that is the y-axis, assuming no shifts. A function is odd if it's symmetric with respect to the origin. Okay, so we'll talk more about origin symmetry here in a second. Let's go back and talk about an even function. Like we said, a parabola is a nice, probably the easiest function to visualize being even. Okay, so graphically, if I give you a picture of a graph, you should be able to estimate whether it's even or odd based on the graph. Okay, that is how we're going to do it by visually. Now, that's not always the most efficient way to do it, right? What if this thing was shifted just a little bit to the right, 0.1 units to the right? You might visually think it's an even function when it's not. So that's why I want an algebraic test. Here's another way to think about an even function. For every point x, y in the graph, so let's mark a point here. Let's say this point is x, comma, y. Okay, there is a point negative x, comma, y that is also on the graph. So the difference between these 2 points, they have the same y value. The only difference is one has a positive x, one has a negative x. So basically, these 2 x values would have to be at the very same height, negative x, comma, y. Okay? Now, that's a generic point. But for every point on this side of the graph that's positive x, positive y, you have a point over here that has a negative x, positive y. If that's true, then you know this graph, this function is symmetric to the y-axis. So to test this algebraically, here's what we're going to do. We're going to plug negative x into the function and try to get back to our original f of x or our original y. Look what happens. It doesn't matter if you plug in a positive x or a negative x, you should get the same y value. you should get the same f of x each time. All right. Origin symmetry. All right. For every point xy on the graph, the point negative x, negative y is also on the graph. So an odd function is symmetric to the origin. Origin symmetry looks like this. Okay. So instead of just folding it over the x-axis, it's kind of like a double fold. You fold it over the x-axis and over the y-axis. So for example, if I fold it over the y-axis first, this piece up here would come over here. And then if I fold that in half over the x-axis, that red piece would now come down here, and the two pieces of the graph line up on themselves. Okay? Now, that's kind of hard to see visually, especially if it's off just by a little bit. You might think it's an odd function when it's really not. So, another way to say this is that you have a positive xy value here, positive x, positive y, for every one of those points. You have a corresponding point down here that's negative x, negative y. Okay? If that's true for every xy combination, then you know the function is an odd function. Therefore, our algebraic test is right here. We're going to plug in negative x and negative y to try to get back to f of x, right? So if you plug in a negative x and a negative y, you should be able to get right back to the same function. All right, let me show you how this looks algebraically. And there's a little hint here. Writing negative y is the same thing as writing negative f of x. Some students get tripped up with the f of x, so if you want to make every f of x into a y, it might be easier for you to follow. Okay? Let's try some. Notice that even and odd has nothing to do with exponents, right? Students used to think, oh, if I see a x to the fourth, it's even. That's not always true. You can't say that for sure. You have to follow these tests. So I'm going to always do my even test first. You'll see why in a second. So my even test is to plug in a negative x for x. So that notation is going to look like this, and see what happens. If I can get back to my original f of x function, then I know this is an even function. So negative x means everywhere you see an x, make it negative. So I'll kind of color it negative x. So this is going to be a negative x. Okay, to the fourth, minus another negative x here squared plus 2. So what I've done is put the negative x's in, replace those old x's with negative x's. Okay, now let's see what happens. Let's see if I can get this back to my original f of x. The negative 3 out front hasn't been changed. Any negative value taken to the fourth power, to a fourth or a second or a sixth power, that sign's not going to change. So this is going to stay the same as x to the fourth. Minus, same thing over here. Negative x squared is going to be the same thing as just x squared. And then plus 2. So if you can see, I plugged in negative x. I got this. That is the same thing as my original f of x function. Therefore, I can guarantee f of x is an even function. That's all you got to do. Okay. Now there's a reason I'm starting with even functions first. Let me show you. Okay. So again, ignoring the exponent, that doesn't guarantee anything. Let's do our tests. Let's plug in negative x to test whether it's even. So if I plug in a negative x, I get 5 negative x cubed minus 1. Okay? Now, because this is a negative number to an odd exponent now, that is going to change signs. This negative x cubed is going to become negative x cubed. The negative 1 doesn't have an x, so it's not being changed at all. So if I compare this to my original function, I am not back to the same thing. This is not an even function. Okay? It has to be the exact same thing as the function you started with. All right. So not even. So to keep track, I kind of put an x up there to remind me that, nope, this guy's not even. Now, let's go check odd. Now, for an odd function, you have to plug in a negative x and a negative y. Now, here's why I do even first. I already plugged in a negative x. I know what that looks like. I know what that is. So I'm going to kind of piggyback off this. Plugging in a negative x, I know gives me negative 5x cubed minus 1. I already did that work. Plugging in a negative y is just coming over here and making the g of x negative. Again, if you don't like this as g of x, you can just make it a y, if that works better for you. Okay, now my goal is to get back to the original function, right? So with this negative out front, I can multiply both sides by -1. I get g of x. Over here, -5 times -1 is positive 5x cubed. -1 times -1 is +1. And if you look back at the original, I'm still not there. So this thing is not even, it's not odd. We will say that it's neither. So you basically have three options here. You can say it's an even function, it's an odd function, or it's neither odd or even. Okay, let's get another one. I don't know why this one's not displaying right, but I'll write it down. So this one, I wanted to say h of x equals, and we had -x cubed over 3x squared minus 9. All right, so let's go through our process here. Even first. All right, so even, I'm plugging in a -x. I'm going to get negative x cubed over 3 -x squared minus 9. All right, up top, I get a negative out front. -x to the third power is going to change to a negative. That's going to make this positive out front. On the bottom, -x squared doesn't change anything. So this is going to be 3x squared minus 9. As you can see, if I compare that back to my original h of x, it is definitely not the same thing. So this is not even. Let's test for odd. So for the odd, I plug in -x and -y, and I try to get back to my original. I already plugged in -x. I know what that gets me. It gets me x cubed over 3x squared minus 9. Okay. Now, to plug in a -y, I'm going to make it negative. Let me keep my color the same here. I'm going to make it negative h of x, right? Like we did in the last problem, I'm going to multiply both sides by -1. So -1 to this side and -1 to that side, okay? When I do that to the left side, negative times a negative is a positive, so I get h of x. But look what happens over here on the right side. This is where you got to be careful with your algebra. When I multiply a fraction by a negative, that negative can't go to the top and the bottom. A -1 over a -1 is actually a positive one. So I've got to pick, hold on. So I've got to pick where that negative is going to go. Now remember, your goal is to get back to this original equation, right? So I'm going to pick to put it back up into the top. If I take that -1 up to the top, I get a -x cubed up top over a 3x squared minus 9 down low, and I'm back to my original equation, meaning this guy is an odd function. All right, so your goal is to always get back to the original function. That's your goal all the time, all right? Okay, so we've talked about even functions symmetric to the y-axis, odd functions symmetric to the origin. The reason we don't talk about something symmetric to the x-axis right now, well, if you think about it, that would be something symmetric to the x-axis. I said in the beginning, we're talking about functions right now. Anything symmetric to the x-axis is not a function. So there are things symmetric to the x-axis. We're not talking about it in this first chapter because this first chapter is dealing primarily with functions. Okay. We're going to stop there. That is the extent for all we got to do right now. Again, this is important. Your test for even and for odd, right? For even, you're going to plug -x in for x and try to get back to the original function. For odd, you're going to plug in -x and -y, try to get back to the original.